For 76 years, the solar system had 9 planets, until 2005, when NASA dropped a headline that changed everything: 10th planet discovered. This new world was heavier and denser than Pluto. But instead of expanding the list, its discovery became the exact reason Pluto was kicked out of the textbooks just 1 year later. That cosmic disruptor was Eris. Today, we're going to decode how a world frozen at -240 degrees Celsius managed to throw the entire scientific community into chaos, and uncover the mystery of the warm ocean recently detected beneath its surface by the James Webb Space Telescope. Subscribe to the channel to explore the furthest reaches of our universe with me. Starting right now, there is something deeply human about the need to name things, to sort the raw chaos of the natural world into categories, to draw lines between what belongs here and what belongs there, to build a vocabulary precise enough to make the universe feel, at least temporarily, like something that can be understood and held in the mind all at once, rather than an overwhelming flood of phenomena with no structure to organize them. Which is why every culture that ever looked seriously at the night sky eventually arrived at the same basic act of sorting. These lights stay fixed. Those lights wander, and the wandering ones deserve a separate name. The word planet comes from the ancient Greek planetes, meaning simply wanderer, a designation requiring no physical understanding of what these objects were. Only the observational fact that they moved differently from the stars fixed behind them, drifting against that background over days and weeks in patterns the stars never followed. A behavioral distinction sufficient to organize astronomical thinking from Babylon through Greece, through the Islamic Golden Age, through the European Renaissance, giving rise to Mercury, Venus, Mars, Jupiter, and Saturn as the original 5. Their positions tracked with increasing precision across millennia, their names embedded in the days of the week across nearly every culture that developed a calendar precise enough to need them. When Uranus was discovered in 1781 through a telescope, it joined the planetary list without controversy because it fit the existing concept well enough. Slow-moving, sun-orbiting, discovered by instrument rather than eye, but behaviorally consistent with what planet had always meant. And when Neptune was mathematically predicted from perturbations in Uranus's orbit and then directly observed in 1846, it joined too. Its existence inferred before it was seen, a demonstration of the power of gravitational mathematics that raised admiration but no particular questions about classification, because Neptune looked and moved exactly like what everyone already understood a planet to be. When Pluto was found in 1930 by Clyde Tombaugh at the Lowell Observatory in Arizona, it became the 9th planet without any formal vote, without any committee deliberation, without anyone asking whether it actually met a written standard. It qualified because it was there. It orbited the Sun, and planet was the only word the astronomical community possessed for a thing like that. A decision whose informality would take 76 years to fully expose itself as a structural weakness in the entire classification system, underlying one of the most fundamental things humanity thought it knew about its own solar system. The weakness was invisible for as long as the solar system appeared simple enough that the question is, this a planet never arose in any genuinely ambiguous way. But the solar system was never actually that simple. It only appeared so because humanity's ability to see into its outermost regions was limited enough that the complexity stayed hidden. And what was hidden, as it turned out, was something enormous, ancient, and populated far beyond anything the 9-planet model had ever suggested or could accommodate without breaking down entirely. Throughout the 1980s and 90s, a small number of astronomers had begun to suspect that Pluto was the most prominent member of a much larger population of similar objects, orbiting the Sun at enormous distances in a thick belt of material, preserved largely undisturbed. Since the solar system formed, a hypothesis requiring evidence that the instruments of the time could barely begin to provide. The outer solar system is vast enough and its objects faint enough that detecting them requires both large telescopes and image analysis software capable of identifying extremely slow-moving points of light against a background of hundreds of thousands of fixed stars. And both the hardware and the software had to develop considerably before the hypothesis could be tested at the scale needed to understand what was actually out there. When those instruments arrived, in the early 1990s, the evidence came quickly. The first confirmed Kuiper Belt object beyond Pluto was found in 1992 by David Jewett and Jane Liu after 6 years of systematic searching with a 2.2-meter Hawaii, and after that, the detections accelerated rapidly, the catalogue expanding from one object to dozens to hundreds as the surveys improved, including Quaoar, at roughly half Pluto's size, Sedna, whose single orbit takes approximately 11,000 years to complete, and whose distance from the Sun, even at its closest approach, keeps it permanently beyond Neptune's gravitational influence, and a growing number of other bodies, each one adding complexity to a picture increasingly difficult to reconcile with the 9-planet framework that textbooks continued to present as settled and permanent fact. With every new large object found, the same uncomfortable question edged closer to the surface. If all of these objects qualify as planets under the criteria that gave Pluto its status, the solar system has far more planets than anyone thought, and that number will keep growing indefinitely as survey technology improves. But if they do not qualify, then by what logic does Pluto remain in the category they are being excluded from? A question that had circulated quietly in specialist papers for years without forcing a resolution, treated as a problem that could be deferred until someone found a convenient opportunity to address it, right up until the discovery that made deferring it any longer structurally impossible arrived in archived data from a California observatory. Waiting in a 15-month-old photograph for the software that had missed it the first time to be run again with a lower detection threshold. There was also the matter of what Pluto actually was, physically, which had been becoming progressively clearer throughout the 1990s and 2000s as measurements improved and the population of known Kuiper Belt objects grew large enough to provide meaningful comparisons. Pluto turned out to be smaller than the Moon, considerably smaller, with a diameter eventually measured by the New Horizons spacecraft in 2015 at 2,377 kilometers, compared to the Moon's 3,474, and it occupied an orbital region crowded with objects of similar composition and comparable, if generally smaller, scale, the situation, nothing like that of the 8 classical planets, each of which occupied its region in solitary gravitational dominance, and together contained almost all the mass in the solar system outside the Sun itself. Pluto was gravitationally insignificant by any meaningful standard, held in a resonant orbital relationship with Neptune rather than dominating its surroundings the way the word planet had always implicitly suggested. And the growing awareness of this, combined with the growing population of Kuiper Belt objects being catalogued each year, had been making the question of Pluto's status increasingly impossible to answer satisfactorily within the existing informal framework, until the discovery that would finally force the issue arrived. In a part of the solar system so remote that the astronomers looking for it had to design their software specifically to catch something moving slow enough to have been there all along and missed entirely by instruments that had never been calibrated for objects at that kind of distance. Most people, when they picture the solar system, work from the same diagram that has appeared in science textbooks for generations. The Sun at the center, the planets in their rings at evenly spaced intervals, Saturn distinguished by its rings for visual interest, Pluto as a small dot at the outer edge, and then empty space followed by the end of everything. a simplification that has served well enough pedagogically, but that omits something so large and so consequential that calling it an omission understates the problem considerably, since what it leaves out is an entire populated region of the solar system, containing potentially hundreds of thousands of worlds, none of which appear in the diagram, and most of which were entirely unknown to science until within the last few decades. Beyond Neptune, which orbits the Sun at about 30 times the Earth-Sun distance, a distance that light, traveling at 300,000 kilometers per second and fast enough to circle the entire Earth 7 times in a single second, takes about 4 hours to cross. There is a vast, donut-shaped region called the Kuiper Belt, beginning at Neptune's outer orbital boundary and extending to about 50 times the Earth-Sun distance, spanning a volume roughly 20 times wider than the asteroid belt between Mars and Jupiter, and containing somewhere between 20 and 100 times as much material, distributed so thinly across such an enormous expanse that traveling through it would feel nearly indistinguishable from traveling through ordinary empty space, since the objects within it, despite their enormous collective number, are separated from each other by distances measured in millions of kilometers. Within this belt sit hundreds of thousands of objects, at least 100,000 larger than 100 kilometers in diameter, with millions of smaller ones that current surveys have not yet fully characterized, that are among the most chemically primitive bodies in the solar system, formed approximately 4.5 billion years ago from the same cloud of gas and dust that produced the Sun and the planets, but preserved in a condition dramatically closer to their original state than anything in the inner solar system, where material has been repeatedly melted, mixed, differentiated, and remade by the geological and astronomical processes that have operated continuously throughout the solar system's history. Processes that have thoroughly obliterated the chemical record of the solar system's earliest moments across everything from Mercury to Neptune. The temperature in the Kuiper Belt approaches negative 230 degrees Celsius across most of its extent, cold enough that chemical reactions proceed at rates negligible on any human timescale, and geological processes are effectively suspended, making the Kuiper Belt something like a frozen archive of the solar system's earliest chemistry. A library of primordial conditions stored in the cold, the way paper stores ink, where the record of the solar system's formation has been sitting largely intact for 4.5 billion years, waiting for instruments sensitive enough to read it in the kind of detail that reveals not just what is there, but what it means about the conditions that existed when everything began. The scattered disk, where Eris actually resides, overlaps the outer edge of the Kuiper Belt and extends far beyond it, populated by objects flung outward during the early violent period when the giant planets were migrating to their current positions, gravitationally scattered by Neptune into highly eccentric, highly inclined orbits that carry them alternately deep into the outer darkness beyond the Kuiper Belt, and then swinging back inward to relatively close solar approaches, spending most of their enormous orbital periods at distances so extreme that sunlight, already reduced to a tiny fraction of its Earth intensity at Neptune's distance, barely qualifies as illumination, which is where Eris has been orbiting in the cold and silence for the entirety of its 4.5 billion year existence. Its highly tilted orbit, carrying it between the outer reaches of the scattered disk and relatively close encounters with the inner Kuiper Belt on a cycle that takes 559 years to complete. At its current position near the farthest point of its orbit, Eris sits approximately 96 times the Earth-Sun distance from the Sun, roughly 3 times farther out than Pluto's current position, and far enough that light from the Sun takes more than 13 hours to reach it, compared to the 8 minutes that same light takes to reach Earth, a distance so large that a car traveling continuously at highway speed would require approximately 160 million years to cover it, a duration comparable to the entire span of time separating the emergence of the first dinosaurs from the present day. which is the kind of number that demonstrates fairly efficiently that the outer solar system operates in dimensions that ordinary human intuition, built by living on a planet where the farthest point reachable by any means is a few tens of thousands of kilometers away, has no natural tools for processing, and that the fact a team of 3 astronomers with a 1.2-meter telescope managed to find something there at all is itself a remarkable achievement of observational astronomy. The total mass of all the material currently in the Kuiper Belt is estimated to be no more than about 10% of the mass of Earth, a number that seems surprisingly small for a region containing hundreds of thousands of objects. But that reflects the fact that the Kuiper Belt is believed to have lost the vast majority of its original material during the chaotic early period of the solar system's formation, when the orbits of the giant planets were shifting and their gravitational perturbations were ejecting material from the outer solar system at enormous rates, leaving behind only the small fraction that managed to find stable orbital configurations before the giant planets settled into their current positions. Which means that what we see in the Kuiper Belt today is only a remnant of what was once there, a preserved fraction of the original outer solar system material that survived the violence of the solar system's youth. The scattered disk objects like Eris carry an additional layer of history on top of this. They are not simply objects that formed in place and stayed there, but objects that formed in the Kuiper Belt and were subsequently ejected outward by gravitational interactions with Neptune during the period of planetary migration, which means that their chemical composition and internal structure reflect both the primordial conditions of the early outer solar system and the dynamical history of a body that has been gravitationally scattered across a range of distances from the Sun over billions of years, making them, in some respects, even more informationally rich than the classical Kuiper Belt objects that have remained in more stable orbits throughout the solar system's history, and making the study of Eris and objects like it potentially one of the most productive avenues for understanding the sequence of events that shaped the outer solar system into its current configuration. The team that found Eris was conducting a systematic survey of the outer solar system using the Samuel Oschin Schmidt telescope at Palomar Observatory, a 1.2-meter instrument on a mountaintop in the San Bernardino Mountains of Southern California, connected to a wide-field camera and to image analysis software designed by Mike Brown of the California Institute of Technology, alongside his colleagues Chad Trujillo and David Rabinowitz. A survey running since 2001 with the straightforward objective of photographing the same patches of sky on multiple nights, comparing the images, and identifying anything that had shifted position against the fixed stellar background, on the principle that stars stay fixed relative to each other across a single night while objects in the solar system move, and that systematically finding the moving things would build a census of the outer solar system with a completeness that previous searches had never achieved. The software filtered out objects moving slower than 1.5 arcseconds per hour, an arcsecond being 1/3600th of a degree, a unit so small that the full moon spans 1800 arcseconds in width, because very slow-moving objects generated large numbers of false positives in the automated analysis. Objects that appeared to move only because of slight differences in atmospheric conditions between successive images, rather than because they were genuinely shifting their position against the starry background. And filtering them out kept the list of candidates manageable, without, the team believed, causing them to miss anything genuinely worth following up. The reasoning held until Sedna, found in late 2003 at just 1.75 arcseconds per hour, barely above the cutoff, close enough to the threshold that the detection had been marginal and would have been lost entirely if the team had set their threshold even slightly higher, which prompted Brown to ask a question he had previously had little reason to ask: whether something even more distant and even more slowly moving might have been passing through their archived data all along, present in image after image from months or years of accumulated observations, always falling below the threshold, The software was programmed to flag, invisible, by the deliberate design of the very detection system meant to find it. The team went back through their archived images and reprocessed them with a lower threshold. A computationally intensive and time-consuming exercise in retrospective data analysis that required sorting through hundreds of thousands of image comparisons, looking for anything the original processing had quietly discarded. And on January 5th, 2005, at 11:20 in the morning, Pacific Standard Time, the reanalysis found a point of light in images from October 21st, 2003, moving at less than 1 arcsecond per hour, covering less than 3 arcseconds of sky across 3 hours of exposure time. So slow that the original software had categorized it as probable noise and filed it away without a second look 15 months earlier. At a time when no one had yet had reason to question whether the detection threshold was set too high, Brown's call to his wife, immediately after the confirmation, contained words he has recounted in multiple interviews and in his book about the discovery. "I found a planet," which was, at that moment, a genuinely accurate statement under the only definition of planet that existed, since initial measurements suggested the object was at least as large as Pluto, and Pluto was still officially the 9th planet of the solar system, making this object, by the logic of the existing and entirely informal classification system, the 10th, a designation NASA would adopt in its initial public communications about the discovery, and that would circulate through media coverage around the world for the following year with the speed and permanence of established fact. The team nicknamed it Xena, after the fictional warrior princess, played by Lucy Lawless in the television series that was popular at the time, partly for the letter X, which was a nod to the historical Planet X searches that had motivated outer solar system surveys for much of the previous century, and partly because the team simply needed something to call it while the formal classification process ran its course, which turned out to take considerably longer and generate considerably more controversy than anyone involved had initially anticipated. And when they discovered a small moon orbiting it in October 2005 using a newly commissioned adaptive optics system at the Keck telescopes in Hawaii, they nicknamed it Gabrielle, after Xena's companion in the series, a naming convention that contained, buried inside it, a quiet joke whose full form would only become visible when the official names were announced the following year. The public announcement of the discovery came on July 29th, 2005, the same day as the announcement of Makemake, another large Kuiper Belt object found by the same team, and 2 days after a separate Spanish team controversially announced the discovery of Haumea, an object Brown's team had also been tracking, forcing a rapid announcement to establish priority and prevent the discoveries of both Xena and Makemake from being similarly scooped, which meant that within the span of 3 days in late July 2005, the astronomical community and the public simultaneously learned about 3 large outer solar system objects comparable in size to Pluto, a clustering of announcements that made it suddenly and unavoidably clear that the outer solar system was far more populated than the 9-planet model had ever acknowledged or could continue to pretend. The circumstances surrounding the Haumea announcement added a layer of controversy that complicated the already fraught situation. Brown's team had been tracking Haumea for months and held their own discovery data. But a computer at the Sierra Nevada Observatory in Spain had accessed Brown's unprotected observing logs before the Spanish team publicly announced their discovery, a sequence of events generating significant dispute about priority and scientific conduct, ultimately resolved in a manner that satisfied few of the parties involved and that added a note of interpersonal discord to the scientific discord that Eris was simultaneously creating at the level of planetary classification, making the summer of 2005 one of the more chaotic periods in the history of outer solar system astronomy, with priority disputes, rushed announcements, and a growing pile of Pluto-sized objects all arriving at once. The practical consequence of all of this was that within less than a year of its discovery, Xena had forced a confrontation that the astronomical community had been successfully avoiding for a decade, by the simple means of being too large, too Pluto-like, and too clearly a member of a large and growing population of similar objects for anyone to continue treating Pluto's planetary status as settled. And the IAU, which had managed to avoid formally defining planet for the entirety of its 87 years of existence, could no longer defer the question without effectively allowing the solar system's planet count to increase indefinitely as surveys improved, which was a situation no one in the field found acceptable. Before the argument in Prague and the vote that settled it, the physical character of Eris itself deserves attention. What its surface is actually like, what conditions operate there, what its existence in the scattered disk has made of it over 4.5 billion years. Because understanding the object that forced the definitional crisis makes the crisis itself more comprehensible. And because Eris turns out to be, by almost any measure, a stranger and more remarkable world than the stripped-down label dwarf planet suggests. A world with a physical character that reflects both the extreme conditions of the outer solar system and the internal dynamics that JWST observations would reveal to be operating beneath its frozen exterior. Eris has a diameter of approximately 2,326 kilometers, measured through stellar occultation, the technique of monitoring a distant star and timing precisely how long Eris takes to pass in front of it and block the starlight. Then, using the duration combined with the known orbital speed to calculate diameter, since no spacecraft has ever been sent anywhere near it, making it the largest object in the solar system that has never been visited by any probe, with everything known about it inferred from measurements taken across a distance that light itself takes more than 9 hours to cross at its current position. A constraint that makes every piece of confirmed information about Eris a considerable achievement of remote observational astronomy. That diameter makes Eris essentially the same size as Pluto, which measures 2,377 kilometers across, a difference of 51 kilometers, roughly the width of a medium-sized city, with each of them covering a surface area comparable to the landmass of South America, and each appearing, if the Earth was scaled to the size of a nickel, roughly as large as a single kernel of popcorn, which provides some sense of the relative scales involved when discussing objects that nonetheless manage to destabilize the entire classification system of planetary science simply by existing in large enough numbers and being discovered in rapid enough succession. The more significant physical difference between Eris and Pluto is in mass. Eris is approximately 27% more massive than Pluto, despite occupying nearly the same volume, because Eris contains a higher proportion of dense, rocky material relative to lighter ices, estimated at roughly 70% rock by mass, compared to Pluto's approximately 50 to 60%. A denser internal composition with direct consequences for the kind of geochemical processes that may have operated in the object's interior across its 4.5 billion year history. Processes that observations published in 2024 would reveal to be far more significant than the prevailing assumption of outer solar system inertness had ever accounted for. The surface of Eris reflects approximately 96% of all sunlight that reaches it, an albedo exceeding that of fresh snow on Earth, which reflects between 80 and 90%, making Eris the second most reflective object in the solar system overall, exceeded only by Enceladus, Saturn's small ice-covered moon whose surface is continuously resurfaced by active geysers erupting from its interior. And the reason for this extraordinary reflectivity is the 559-year cycle of Eris's orbit, which carries it between approximately 38 times the Earth-Sun distance at closest approach, and nearly 98 times that distance at its farthest point, a swing so extreme that the object's surface undergoes a complete atmospheric cycle with every orbit, cycling between frozen stillness and brief atmospheric activity in a rhythm driven entirely by the changing distance from the Sun. At the close end of this orbit, the surface warms enough, relative to its extreme cold at all other times, for the methane and nitrogen ice to sublimate directly into a thin, tenuous atmosphere that briefly hovers above the surface before the orbit carries Eris back outward, and the falling temperature causes that atmosphere to refreeze and fall back to the ground as an extremely thin, uniform coating of fresh methane and nitrogen ice, covering whatever darker organic material might have accumulated in the intervening decades and resetting the surface to brilliant white with every orbit. Which is why Eris, unlike Pluto with its varied reddish patches of accumulated tholins, marking regions where organic compounds have built up over time, presents a face almost perfectly uniform in its reflectivity. A world that continuously buries its own surface history under new ice and starts the cycle again every half millennium. The surface temperature ranges from approximately -243 degrees Celsius at its farthest point to approximately -217 degrees Celsius at its closest, a range in which the coldest temperature ever recorded on Earth's surface, -89.2 degrees Celsius, measured at a Soviet Antarctic research station in 1983, would register as comparatively warm, and in which methane, the gas that burns in kitchen stoves and constitutes the primary component of natural gas, and nitrogen, which makes up about 78% of the air being breathed right now, and which becomes liquid only when cooled to -196 degrees Celsius. Both exist as solid ice, as rigid and structural as any rock. Eris has one known moon, Dysnomia, orbiting it every 15.78 Earth days at a distance of about 37,000 kilometers, roughly 1/10 the Earth-Moon distance of 384,000 kilometers, which means that from the surface of Eris, Dysnomia would appear significantly larger in the sky than the Moon appears from Earth, completing its orbit in just over 2 weeks rather than the 29.5 days the Moon takes. And the two bodies are gravitationally locked to each other in double synchronous rotation, each permanently keeping the same face turned toward the other, a configuration shared in the solar system only by Pluto and its moon Charon, one of several physical parallels between the two objects that makes understanding one consistently illuminate the other, as though the outer solar system had produced a pair of near-identical worlds and placed them in vastly different orbital environments to serve as natural comparison cases for anyone who wanted to understand what the scattered disk actually does to the objects it contains. From the surface of Eris, the sky would be absolute and unfiltered black, the Milky Way overhead in a resolution and density that atmospheric scattering on Earth always prevents, visible in the kind of clarity and completeness that no terrestrial observer has ever experienced, since even the darkest Earth-based sky site always introduces some atmospheric interference, and the Sun reduced to the brightest point of light in an otherwise unchanged night sky, still capable of damaging unprotected eyes, but visually just a star, a point rather than a disk, providing illumination at approximately 1/10,000th of the intensity it delivers to Earth's surface. A faint reminder of a heat source, 9 hours away that barely registers on a thermometer, reading -240 degrees. A view that has remained essentially unchanged for the entirety of the 4.5 billion years. This object has been making its long, slow, tilted orbits through the dark. The International Astronomical Union, founded in 1919, is the organization governing the naming and classification of astronomical objects, representing roughly 10,000 professional astronomers across more than 80 countries and convening a General Assembly every 3 years to pass resolutions that become for practical purposes, the official scientific consensus on whatever questions they address. Resolutions carrying no legal force but representing the closest approximation to a shared global standard that the astronomical community possesses, which for most of the IAU's 87 years of existence had been entirely sufficient, because the questions it addressed had generally been technical enough that the absence of a formal definition of planet at the center of its most visible work was simply never a problem. Anyone was forced to confront directly. The 2006 General Assembly in Prague had been anticipated with unusual tension because Eris had made the definitional question impossible to continue deferring. The astronomical community had managed to avoid formally defining planet for the entire history of organized astronomy, relying on an informal consensus that had held as long as nothing ambiguous enough to challenge it had been found. And the discovery of Eris, an object comparable in size and composition to Pluto and residing in a similar region of the outer solar system, had destroyed the conditions under which that informal consensus could continue to function, since there was simply no principled way to call Pluto a planet without also calling Eris one. And calling both of them planets meant calling dozens of other known outer solar system objects planets, which meant the word planet would cease to encode any meaningful physical distinction within a few years of improved survey coverage. The IAU formed a planet definition committee of 7 people: astronomers, a historian of science, and a science communicator, in the spring of 2006, asking them to produce a formal definition in time for the August meeting. A task the committee's chair, Owen Gingerick, described afterward as one in which several members admitted they had spent nights unable to sleep, unable to stop worrying that the 2 days of meetings in Paris in late June would end without consensus on a question that had resisted resolution for decades because it was, at its core, not purely a scientific question but also a conceptual one about what kind of distinction the word planet was meant to be drawing. The committee's initial proposal, presented to the assembled astronomers on August 16th, defined a planet as any object orbiting the Sun with sufficient mass for its own gravity to have compressed it into a roughly spherical shape, a criterion that would have immediately expanded the solar system to 12 planets by adding Ceres, the largest object in the asteroid belt between Mars and Jupiter, Eris, and even Charon, Pluto's largest moon, whose center of mass with Pluto lies outside Pluto's surface, arguably making the pair a double planet system rather than a planet-moon pair, a proposal that generated immediate and intense debate, because its most obvious consequence was that the solar system's planet count would continue growing indefinitely as surveys improved, with at least a dozen additional candidates already known and dozens more almost certainly waiting to be found, and no principled mechanism under the proposed criteria to stop the list from eventually reaching 50 or 100, at which point the word planet would have ceased to encode any meaningful physical distinction and would mean nothing more than round thing orbiting the Sun. The competing proposal that gained decisive traction in 2 open meetings on August 22nd added a third criterion to the first 2. The object must have cleared the neighborhood around its orbit of other bodies, meaning its gravity must have become dominant in the region it occupies, having absorbed or ejected the competing material that once shared its orbital path over the course of the solar system's history, a criterion that encoded a genuine physical distinction between objects like Jupiter, which is more than 2.5 times more massive than all the other planets combined and has shaped the gravitational structure of everything around it for 4.5 billion years, and objects like Pluto, which shares its orbital region with thousands of Kuiper Belt objects of comparable size and composition, and has established gravitational dominance over none of them, a difference of physical kind rather than merely degree, and one that reflected something real and important about the solar system's architecture rather than simply imposing an administrative boundary for the convenience of classification. On August 24th, The last day of the 10-day conference, 424 people voted, fewer than 5% of the IAU's total membership of roughly 10,000. With many of the approximately 2,500 total conference attendees already having departed for home before the final session, and with several of the most prominent planetary scientists in the field absent from Prague entirely, having been unable to attend or having left earlier in the week. And one attendee, speaking to reporters immediately after the result was announced, described the situation in terms that circulated widely. "I'm embarrassed for astronomy. Less than 5% of the world's astronomers voted." A criticism joined in the following weeks by equally pointed objections from scientists who had been present but disagreed with the outcome, from others who had been absent and felt the process had moved too quickly, on a question with consequences too broad to be settled in. The three criteria definition passed regardless, reducing the solar system from 9 planets to 8 by designating Pluto, Eris, and Ceres as dwarf planets. A category the IAU explicitly stated was separate from and subordinate to the category of planet rather than a subcategory of it. And 2 weeks later, on September 13th, the object received the name that fit it with an almost uncomfortable precision, Eris, after the ancient Greek goddess of discord and strife who, according to mythology, had been excluded from a wedding on Olympus and in retaliation rolled a golden apple, inscribed for the most beautiful among the attending goddesses, setting off the chain of vanity and competition that escalated into the Trojan War. A goddess who caused civilizational chaos, simply by showing up somewhere unexpected and making a question visible that everyone would have preferred to leave unasked. With the moon named Dysnomia, the demon goddess of lawlessness and daughter of Eris in Greek mythology, a name that also contained, for those who knew to look for it, the quiet joke that the actress who had played Xena on television was named Lucy Lawless. The public response to Pluto's reclassification was extraordinary by the standards of any scientific announcement, and it revealed something about the relationship between scientific knowledge and cultural identity that the astronomers who made the decision had perhaps not fully weighed. The fact that scientists develop a professional relationship with revision, an ability to hold classifications with appropriate tentativeness and release them when better frameworks emerge, is a habit acquired through years of training and practice. And the majority of people who had learned the 9 planets in elementary school had acquired them the way children acquire foundational facts, as settled features of reality rather than provisional approximations, which is a different and considerably more adhesive form of knowing that does not dissolve, simply because the logic behind the update is sound, however clearly it is explained, and however straightforwardly it follows from the evidence. Pluto had been the 9th planet for 76 years, 3 complete generations, and everyone who had been through any form of science education anywhere in the world since 1930 had encountered the sequence: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto as a basic fact about the universe, memorized it, been tested on it, and filed it alongside other foundational certainties in the mental architecture of their understanding of the cosmos, which meant that when it changed, it did not feel like a scientific update. It felt like something that had been true for a lifetime was being retroactively declared false. A genuinely disorienting experience whose psychological cost the correctness of the underlying science did little to reduce, and that the compressed timeline of the Prague vote, a week of debate followed by an afternoon vote on the last day of a conference, did nothing to soften. Children, whose relationship with classroom knowledge lacks the intellectual distance adults cultivate through years of watching scientific consensus shift in the news and in textbook revisions, responded with the directness that children reliably bring to situations adults are managing with more diplomatic language, writing hundreds of letters to astronomers, planetarium directors, science museums, and newspaper editors, calling the IAU planet killers, demanding Pluto's reinstatement on grounds ranging from the scientific to the sentimental, to simply the assertion that 76 years of being called a planet should carry some weight in the deliberation. While the American Museum of Natural History in New York, whose director Neil deGrasse Tyson had quietly removed Pluto from the museum's planetary display as early as the year 2000, had already been receiving angry mail from school children about that earlier decision for 6 years, and found the volume increase substantially after the Prague vote made the reclassification official at the international level. The legislative response was, in its own way, the most revealing evidence of how deeply the 9-planet model had embedded itself as cultural fact in the public consciousness of at least one country, the state legislature of New Mexico, where Clyde Tombaugh had lived and worked for much of his career at New Mexico State University after his initial discovery at the Lowell Observatory in Arizona, and whose ashes had been placed aboard the New Horizons spacecraft launched toward Pluto in January 2006. Passed a resolution in 2007 declaring Pluto a planet whenever it passed through New Mexico airspace. Illinois passed a similar resolution in 2009, and California's legislature went further, passing a resolution that described the IAU's decision as mean-spirited and expressed solidarity with Pluto on behalf of the people of the state, noting that Pluto shared its name with a famous animated dog associated with a California entertainment company. A document demonstrating that at least 54 California legislators held opinions about dwarf planet classification strong enough to act on them in an official governmental capacity. The American Dialect Society chose Pluto as its word of the year for 2006, defined as to demote or devalue someone or something. As happened to the former planet Pluto, when the General Assembly of the International Astronomical Union decided Pluto no longer met its definition of a planet, with the Society's president observing that the choice reflected the intensity of the public's emotional reaction to the news, which he described as demonstrating the importance of Pluto as a name in the collective imagination, the word spreading quickly into broader usage as shorthand for any demotion or downgrading that felt unjust or arbitrary. An unusual fate for a piece of astronomical nomenclature, and a fairly accurate measure of how far beyond the boundaries of professional astronomy. The cultural consequences of a single afternoon vote in Prague had managed to travel in the Prague, months following the decision. Venetia Burney Fair, the woman who, at 11 years old in 1930, had suggested the name Pluto to her grandfather, a retired Oxford librarian who passed the suggestion to the Lowell Observatory, where it was immediately accepted as the most fitting among the many proposals received, making her the only living person in the world who had given a name to something that was, for a significant portion of a century, an official planet in the solar system. Received the news of Pluto's reclassification with equanimity when interviewed by the BBC at the age of 87, noting simply that the object itself remained unchanged regardless of its classification, which was true in every physical sense, and which captured with quiet precision the essential point that Eris had demonstrated so effectively by existing. The solar system had always been what it actually was, and what changed in Prague was only the accuracy of the human description applied to it. The scientific community itself was divided in ways that persisted long after the vote, with a significant faction of planetary scientists continuing to argue that the 3 criteria definition was both scientifically flawed and procedurally illegitimate, that the clearing the neighborhood criterion was poorly defined and created its own ambiguities, and that the process by which it was adopted, rushed, poorly attended, and conducted without adequate consultation of the broader planetary science community. failed to meet the standards that a decision of that magnitude deserved. The debate about whether to revise the definition has continued at every IAU General Assembly since 2006, with alternative proposals circulating regularly and the question of whether dwarf planets should be considered a subcategory of planets or a fundamentally distinct class, remaining unresolved to the satisfaction of everyone involved. Mike Brown himself, in the years following the Prague vote, described himself with a mixture of genuine amusement and genuine philosophical acceptance as the person who had killed Pluto. Adopted the Twitter handle Pluto Killer as a kind of dark joke about the consequences of discovery, and wrote a book titled How I Killed Pluto and Why It Had It Coming, which captured something real about the situation, which is that the demotion of Pluto was not an arbitrary act of institutional hostility toward a beloved object, but a necessary consequence of the fact that the outer solar system is what it actually is: populated and complex, and categorically different from what the 9-planet model had suggested, and that Pluto's status as a planet had always rested on ignorance of that complexity rather than on any physical property that distinguished it from its neighbors. What gets consistently lost in the story of Pluto's demotion, in the anger and the letter writing and the legislative resolutions and the cultural noise that surrounded the Prague decision and continued for years afterward, is that the reclassification did the opposite of what it emotionally felt like it had done, not diminishing the solar system by removing one of its planets but revealing a solar system vastly larger, more populated, more dynamically complex, and more scientifically interesting than the 9-planet model had ever been able to accommodate. By finally allowing the structure that had always existed to be described accurately, rather than conveniently simplified into a form that fit the limits of what instruments had previously been able to find. The third criterion, clearing the neighborhood, encodes a genuine, physically meaningful distinction that the informal definition had been obscuring for decades, between objects whose gravity has shaped and continues to shape the large-scale structure of the solar system around them, at scales spanning billions of kilometers and billions of years, and objects that are themselves shaped by the gravitational environment they inhabit, without meaningfully shaping it in return. A distinction that matters profoundly for understanding how the solar system formed, why its regions are structured the way they are, and how the various populations of objects within it relate to each other across geological timescales. Jupiter is more than 2.5 times more massive than all the other planets combined, a mass so dominant that its gravitational influence has been operating across the inner solar system for 4.5 billion years, preventing the material in the asteroid belt between Mars and Jupiter from ever coalescing into a planet, deflecting comets onto trajectories that carry them away from the inner solar system rather than toward it, at rates that would otherwise be far more devastating for the rocky inner planets, and in some models of solar system formation, playing a critical role in creating the stability conditions that allowed complex life to emerge on Earth by moderating the bombardment rate that Earth's surface was subjected to during the solar system's chaotic early history. While Pluto, roughly 65,000 times less massive than Neptune, and sharing its orbital region with thousands of Kuiper Belt objects of comparable size and composition, has never gravitationally dominated anything around it. A physical difference of kind rather than degree that the 3 criteria definition describes accurately, and that the informal definition had simply been too imprecise to capture. Once that distinction was formally recognized, the solar system that came into focus contained 8 gravitationally dominant planets, surrounded by a vast outer region populated by potentially hundreds of thousands of smaller worlds. 5 officially recognized dwarf planets in Pluto: Eris, Ceres, Makemake, and Haumea, with dozens of additional strong candidates awaiting formal evaluation, and best current estimates suggesting the Kuiper Belt and scattered disk together may contain hundreds of additional dwarf planet-sized objects that current instruments have yet to characterize. orbiting in the cold at distances that make their detection extraordinarily difficult, even with the most powerful telescopes available. A census of the outer solar system that is almost certainly orders of magnitude more complete today than it was in 1930, and that will continue expanding as survey technology improves. Each new discovery adding detail to a picture that is simultaneously more accurate and more surprising than the 9-planet model it replaced. David Jewett, who spent 6 years searching before finding the first confirmed Kuiper Belt object in 1992, and who has spent the decades since building the field of outer solar system science into one of the most active and productive areas of planetary research, described the trade with a precision that captures the real significance of what changed in 2006. We have discovered -1 planet and +1 Kuiper Belt. It seems like fair trade to me. A formulation that gets at what the reclassification actually accomplished, which was to replace a convenient simplification with an accurate description of a far more interesting reality, revealing Pluto and Eris as the most prominent known members of a family of ancient worlds that carry, in their preserved chemistry and largely unaltered structure, the record of the solar system's formation in a way nothing in the inner solar system can, simply because they have changed so little in 4.5 billion years that they remain readable as documents of initial conditions, rather than as the products of the geological and chemical processing that has overwritten those conditions everywhere closer to the Sun. The structural shift in how the solar system is understood extends beyond the simple addition of a new category to the classification system. The recognition that the outer solar system is populated with hundreds of thousands of worlds changes the picture of what the solar system actually is at a fundamental level, from a small collection of dominant planets surrounded by relatively minor debris to a system with a vast, complex outer architecture that contains more total objects than the inner solar system by orders of magnitude, most of them chemically pristine and structurally preserved in ways that make them invaluable for understanding the earliest phases of solar system formation. Phases that the geological activity of the inner solar system has made impossible to read from the surfaces of Earth, Mars, Venus, or Mercury. The irony of Pluto's reclassification, viewed from this angle, is that it elevated rather than diminished what Pluto actually is. From a small, anomalous planet at the edge of the solar system, a minor embarrassment to the planetary model that planetary scientists had been trying to explain away for decades, to the prototype of an entirely new and scientifically significant class of objects, the most prominent and best-studied member of a population whose investigation is now one of the most productive frontiers in planetary science, a status that is objectively more interesting and more scientifically meaningful than smallest planet ever was, even if it comes without the cultural cachet of the 9-planet model that 3 generations of schoolchildren had memorized. The working assumption for most of the time astronomers had been aware of the Kuiper Belt was that its objects were essentially geological fossils. Cold, chemically inert, structurally static remnants of the primordial solar system whose scientific value lay precisely in their preservation, in the fact that the extreme cold of the outer solar system had kept them essentially unchanged since they formed, making them readable records of initial conditions that the geological and chemical activity of the inner solar system had long since obliterated everywhere else. An assumption so widely shared, and apparently so obviously correct given the temperatures involved, that it was built into the background of outer solar system science as a given rather than a hypothesis, something assumed rather than tested, a starting point for research rather than a question requiring investigation. In February of 2024, a team led by Christopher Glane of the Southwest Research Institute published 2 papers in the journal Icarus that showed the assumption was significantly wrong for Eris and the closely related dwarf planet Makemake, using data from the James Webb Space Telescope, the largest and most powerful space observatory ever built. Launched in December 2021 and beginning its scientific operations in the following year, to observe both objects in wavelengths that earlier telescopes, including the Hubble Space Telescope, had been unable to access with sufficient sensitivity to detect the specific chemical signatures the team was looking for. The key measurement was the ratio of deuterium to ordinary hydrogen in the methane ice on the surfaces of both objects. Deuterium being a heavier isotope of hydrogen containing one neutron in addition to the single proton of ordinary hydrogen, a form of hydrogen present in the universe since the Big Bang and distributed in proportions that vary depending on the physical and chemical history of the substance containing it, making the deuterium to hydrogen ratio in a given substance a chemical signature of its origin and history that is difficult to alter after the fact and relatively straightforward to interpret once measured with sufficient precision. Since different formation environments and different chemical processes produce methane with characteristically different isotopic fingerprints, methane preserved unchanged from the early solar system's primordial material. Methane that formed in the solar nebula before the planets were assembled and has been sitting unaltered on a cold surface ever since, would carry a substantially higher deuterium to hydrogen ratio than methane generated geochemically inside a warm planetary body, where reactions between water and carbon-bearing rock at elevated temperatures produce methane whose isotopic composition reflects the conditions of that internal geochemical environment rather than the conditions of the original solar nebula, making it possible, in principle, to determine by isotopic measurement alone whether the methane on the surface of a distant outer solar system object arrived there as primordial material or was produced internally and subsequently delivered to the surface through some kind of geological process. What the James Webb observations revealed was that the methane on the surface of Eris carries a deuterium to hydrogen ratio inconsistent with primordial preservation, lower than primordial methane would produce, matching instead the signature of methane generated geochemically from reactions between water and carbon-bearing rock at temperatures above approximately 150 degrees Celsius, somewhere inside the object, which is hotter than boiling water at standard atmospheric pressure on Earth, a temperature more associated with industrial chemical processing or hydrothermal geological activity than with anything expected to exist inside a frozen world, sitting nearly 100 times the Earth-Sun distance from the Sun, whose surface temperature hovers around -240 degrees Celsius at its current position. The energy source for this internal heat is radioactive decay in the rocky core, the slow, continuous release of heat from decaying uranium, thorium, and potassium isotopes present in the rocky material of Eris's interior. The same fundamental process that drives plate tectonics and volcanic activity on Earth, which had been assumed insufficient in a body the size of Eris to generate temperatures of any geological significance. Since Eris contains far less radioactive material in total than Earth does, simply by virtue of being smaller, but which the James Webb data directly contradict by indicating that Eris's rocky core reached temperatures sufficient to produce geochemical methane at some point in the object's history. Temperatures that also imply, by the same physics, the possibility of liquid water existing at the boundary between the rocky core and the overlying ice mantle, a subsurface ocean hidden beneath kilometers of frozen surface, insulated from the extreme cold above by the same layers of ice that make it completely invisible to any external observation. Glein described the situation in the paper as signs of hot times in cool places, a phrase that captures the central paradox with an efficiency that longer descriptions struggle to match, and added in the same publication, after the New Horizons flyby of the Pluto system, and with this discovery, the Kuiper Belt is turning out to be much more alive in terms of hosting dynamic worlds than we would have imagined. A statement that reframes the outer solar system from a cold, static archive of primordial material into something considerably more active, more internally complex, and more potentially consequential for questions about planetary habitability in unexpected environments than the models had ever accounted for. With Eris, the object that forced the definitional crisis in 2006 by simply existing and being found, now also forcing a revision of what it actually means for a world to be frozen, inert, and unchanged at the edge of everything. The possibility of a subsurface ocean on Eris connects it to a class of worlds that has become one of the most intensely studied targets in planetary science. Over the past 2 decades, the ocean worlds, icy moons, and dwarf planets, whose frozen exteriors conceal liquid water, interiors sustained by various forms of internal heating, including Saturn's moon Enceladus, whose active geysers demonstrate ongoing hydrothermal activity, Jupiter's moon Europa, whose subsurface ocean is considered one of the most promising environments for extraterrestrial life in the solar system, and Pluto itself, which New Horizons data suggests may harbor a subsurface ocean of its own, sustained by the same kind of radioactive decay that the James Webb observations now indicate may be operating inside Eris. The significance of this extends beyond the specific case of Eris and Makemake. If 2 randomly selected large Kuiper Belt objects both show evidence of geothermal activity and possible subsurface oceans, it suggests that internal heating and liquid water environments may be common features of large outer solar system objects generally, a conclusion that would fundamentally change the picture of how many potentially habitable environments exist in the solar system and where they are located, shifting the focus of habitability research outward from the traditional habitable zone around the Sun to include a much larger and more distant population of worlds whose interiors are warmed by radioactive decay rather than by proximity. To a star, the story of Eris ends, at least for the present, with a question that the object itself helped make possible to ask: whether the solar system that Eris forced into greater clarity is itself fully visible yet, or whether something larger, farther, and as yet entirely undetected has been shaping the outer reaches of what we can observe from a distance too great for any current instrument to bridge. A question that has been accumulating observational pressure for more than a decade, and that the most powerful sky survey telescope ever built may answer, one way or another, within the next few years. The observation driving the question has been building since the mid-2000s. The objects with the most extreme outer solar system orbits, those carrying them to distances of more than 200 times the Earth-Sun distance, and with single orbital periods spanning thousands of years, cluster in ways that random distribution across the outer solar system would not produce, tending to approach the Sun in the same general region of sky, with orbital planes tilted in similar directions, and several of them on trajectories twisted roughly 90 degrees out of the plane of the solar system, in a configuration that the known gravitational influences of the 8 classical planets cannot account for, suggesting that some additional gravitational source has been sculpting these orbits from a position the surveys have not yet reached, imposing a structure on the outermost objects of the solar system that should not exist if the 8 known planets are the only large gravitating bodies in the system. In January of 2016, Mike Brown and his colleague Konstantin Batygin at Caltech published a paper in the Astronomical Journal proposing that a single undiscovered planet could account for the pattern an object with a mass somewhere between 5 and 10 times that of Earth, orbiting the Sun at a distance of approximately 400 to 800 times the Earth-Sun distance, on a highly elongated orbit requiring 10,000 to 20,000 years to complete, whose gravitational influence would, through the same resonance mechanisms by which Neptune organized the Kuiper Belt's resonant objects into their current configurations over billions of years of slow gravitational interaction, have been gradually pulling the most distant trans-Neptunian objects into the clustering pattern the surveys were detecting, a hypothesis they called Planet 9 that generated immediate and intense discussion in the planetary science community and that has been continuously refined as new data from ongoing outer solar system surveys has arrived. The evidence for the hypothesis has accumulated in multiple independent lines over the decade since the original paper. The clustering of extreme trans-Neptunian object orbits has been confirmed in successive analyses as more such objects have been found. Several objects have been discovered on orbits twisted far out of the plane of the solar system, in configurations that Planet 9's gravity would produce, and a 2024 paper by Brown and Batygin analyzing the orbits of 17 extreme trans-Neptunian objects described the accumulated statistical evidence as the strongest case yet assembled for the planet's existence. With early 2025 simulations by a separate group at Princeton, refining the mass estimate to approximately 4.4 times that of Earth, somewhat smaller than the original prediction of 5 to 10 Earth masses, but still firmly within the range of an object that would qualify as a genuine planet by classical standards. And that would have been the most prominent undiscovered object in the solar system since Neptune. The competing interpretation that the clustering is an artifact of observational bias rather than evidence of a real object, a consequence of the fact that surveys tend to observe certain parts of the sky more frequently than others, and thus produce a distribution of detected objects that looks structured simply because it is incompletely sampled, has been maintained with equal persistence by other groups, analyzing the same datasets with different assumptions about survey completeness. And the debate between the two interpretations has been conducted with the kind of sustained intensity and methodological disagreement that indicates genuine scientific uncertainty, rather than a question with a clear answer that one side is simply failing to acknowledge, which is precisely the kind of situation that requires more data to resolve, rather than more sophisticated analysis of the data already available. A separate paper published in October 2025, led by Princeton astrophysicist Amir Siraj, proposed the existence of a different additional body in the outer solar system, somewhere between the mass of Mercury and the mass of Earth, orbiting closer in at approximately 80 to a few hundred times the Earth-Sun distance, based on a different observation, the Kuiper Belt itself, at distances beyond about 80 times the Earth-Sun distance, appears tilted by approximately 15 degrees relative to the plane of the solar system. A structural anomaly in the distribution of Kuiper Belt objects that cannot be accounted for by the gravitational influence of the 8 known planets, and that a moderately massive body in the right part of the outer solar system could plausibly produce, with the two hypotheses being entirely compatible in the sense that Planet 9 and Planet Y, as Siraj's team called it, could both exist simultaneously as separate objects at different distances, producing different measurable effects on the outer solar system's structure. The Vera C. Rubin Observatory in Chile, which houses a 3,200 megapixel camera, the world's largest digital camera, capable of photographing the entire available southern sky every few nights, began scientific operations in late 2025 and will produce thousands of new outer solar system detections over the coming years, building a statistical sample large enough to test the clustering patterns the Planet 9 hypothesis depends on, with a completeness that no previous survey has been able to achieve. With Brown describing the possible outcomes in binary terms, either Rubin finds Planet 9 directly in its sky survey images, confirming the hypothesis in the most direct way possible, or the new population of outer solar system objects it discovers tests the statistical case so thoroughly that the question of the planet's existence is settled within a few years of operation, with the answer going one way or the other based on whether the clustering pattern holds up or dissolves, when the sample size increases by the orders of magnitude that Rubin's sky coverage will provide. The historical parallel is worth noting. Neptune was predicted from gravitational perturbations in Uranus's orbit in 1845 and directly observed in 1846, establishing the method of inferring the existence of unseen bodies from their gravitational signatures on visible ones as a viable and powerful tool of planetary science. The same method Brown and Batygin are applying to the outer solar system more than a century and a half later. And if Planet 9 is eventually found, it will be the first time since Neptune that a planet was predicted from gravitational evidence before being directly seen. An echo across nearly 2 centuries that closes a loop running directly from the discovery of Eris in 2005. Through the definitional crisis it created in 2006, through the richer understanding of the outer solar system that emerged from that crisis, and finally to the realization that even the richer understanding may be missing something enormous, hiding in the dark beyond everything that has been found so far, patient and cold and indifferent to the arguments being conducted about it on the other side of the solar system. What Eris ultimately demonstrated is that the boundaries humanity draws around the natural world are always, at some level, confessions of incomplete knowledge, lines drawn at the edge of what instruments can see rather than at the edge of what actually exists, held in place by consensus and inertia until something arrives that the existing lines cannot accommodate, at which point the choice between expanding the map and pretending the anomaly away becomes impossible to defer. The solar system did not change in August of 2006. The objects beyond Neptune were always there, always numerous, always ancient, always more geologically complex than anyone had assumed. What changed was only the honesty of the description, the willingness, forced by a slow-moving point of light in a 15-month-old photograph, to replace a convenient story with an accurate one, and to accept that accuracy, in this case, came with the cost of a classification that 3 generations of schoolchildren had memorized as permanent fact. Every map has an edge where the known gives way to inference, and beyond inference to genuine darkness. The outer solar system is that edge for human knowledge right now. And somewhere in that darkness, if the orbital mathematics holds, something large is still waiting to be found, patient and cold and indifferent to whether anyone ever names it.